Hello, I'm Sebastian, and I'm going to be presenting our work on building resource allocators that hide how many resources and which resources are allocated and to whom. So this work is in collaboration with Sampath and with Zach. And just for context, this work is in the general area of preventing side channel attacks, although there are some key differences, which I'll get into. So let me just start by briefly reviewing side channels. When an application consumes resources, for example, when the application has a CPU to execute instructions, or when the application sends or receives a file on the network or accesses memory, the consumption of these resources can leak information to other entities in the system and actually even outside the system. And as one example, the rate at which your battery drains or your CPU fan spins can leak information about the kind of computation that you're performing. So if the fan is spinning very fast, then perhaps the task that you're running is CPU intensive. Similarly, the size of messages that you send on the network or your memory access pattern can also leak information. So all of these side channels are fairly well known, and we have defenses to address them, including things like padding requests, using constant time operations, accessing memory using oblivious RAM, and so on. In this work, however, we are not concerned with the information that leaks when resources are consumed. In other words, the previous side channels that I just showed you are orthogonal to the goals of this project. Instead, we are interested in the information that leaks when resources are allocated, which is an event that happens before the consumption of the resources take place. So just to give you a concrete example, suppose that you have two users, Alice and Bob, who want to talk with each other using a messaging app like Skype. So in order to start a conversation in this app, Alice is going to use a dialing protocol to notify Bob of her intention to start a conversation. So she'll send a dial request. And at this point, Bob is going to pick up the call, which essentially allocates a communication channel between Alice and Bob that they can use to start talking. Now, imagine a slightly different scenario in which at the same time that Alice calls Bob, some other user, Charlie, also happens to call Bob. So in this case, the app will likely keep some kind of queue that stores the incoming requests. And then using a resource allocation policy, for example, FIFO, first in, first out, the app is going to allocate a communication channel to the first request, which in this case, it's Alice. Now, one thing to keep in mind is that in a system like Skype, you can only have one video chat at a time. Actually, this is also true of Zoom. So there's only one communication channel, which is a limited resource in this case. So what happens with Charlie is that, well, Charlie's out of luck, right? His request is ignored, or he's just gonna get a busy signal saying sorry. So the problem in this scenario is that if Charlie is the adversary, he basically learns that Bob is talking to someone else because he was not allocated the resource that he requested. In other words, he was not given the communication channel. And while this might not be a big deal for Skype because this was never part of Skype's threat model, this is actually a big problem in anonymous messaging systems because this attack actually enables other attacks called traffic analysis attacks, such as intersection and statistical disclosure attacks, which anonymous communication systems were meant to prevent in the first place. So in fact, to my knowledge, every metadata private messaging system that has been proposed in the literature is actually vulnerable to this type of allocation-based side channel. Now, I'm not going to dwell on this too much, but I do want to point out that resource allocators are everywhere. So things like, how you assign virtual machines to servers, or how do you allocate network bandwidth to virtual machines. So if you are concerned about side channels, it might actually be worth revisiting what information, if any, your allocators in the systems that you use leak, and to whom do they leak that information. With that said, in the rest of this talk, I'm going to formalize what makes an allocator private. And then I'm going to discuss why existing allocators, for example, the FIFO allocator using the messaging app that I just described, fails to guarantee privacy. And then I'm going to go over some of our constructions and conclude with a short discussion. So we start with a resource that has a capacity that is finite and public. So in this case, I chose a cake, and there's a limited number of slices. And we also have processes here at the bottom, which are the entities that want to consume the resource. So these processes want to get a slice of cake so they can eat it. And finally, we have a resource allocator, which is an algorithm that's going to determine how to assign cakes to processes. So if we think of time as happening in discrete rounds, then in every round, some subset of the processes are going to ask for a slice of cake, and the allocator will assign the slices of cakes however it sees fits. So in this particular case, it gives process 1 a slice of cake and gives process 2 nothing. And the way we're going to define privacy is with a notion that we call allocation indistinguishability. So suppose that we have 2 slices of cake. Those are our limited resource. And suppose that we have a set of processes that are actively requesting a cake in the current round. So these 3 processes that I'm showing here are going to be a subset of all possible processes in the system. And these ones are the active ones. And a subset of these active processes are going to be compromised by the adversary. And I'm going to call those processes the malicious processes, which I'm denoting with this red box. And we're going to call the remaining processes the honest processes. Note that the allocator doesn't actually know which processes are malicious or honest. This is completely invisible to what the allocator does. And we're going to say that an allocator is private if the distribution of allocations given to malicious processes in a universe in which the adversary controls some, but not necessarily all of the active processes, meaning in a universe that looks kind of like this, is indistinguishable from the distribution of allocations given to malicious processes in a universe in which the adversary controls all of the active processes. So a universe that looks like the one on the right. So in other words, if the adversary cannot distinguish between these 2 universes, then what it means is that by observing its own allocation, it cannot determine whether any honest processes requested a resource or not. And so this is how we capture our goal of privacy. Of course, privacy is actually very easy to achieve if the allocator outputs nothing. But this kind of allocator is useless in practice. So we're going to introduce an additional requirement, which we call liveness, which basically says that the allocator should sometimes allocate resources to at least one process. And by sometimes, what we mean is that the probability of at least one process getting a resource should be non-negligible. So let me now take a look at some of the obvious allocators that you might consider and discuss why they fail to achieve our definition of privacy. So let's start with FIFO. So let's assume the adversary compromises the first and the third process, and the order of processes in the queue is given vertically. So a FIFO allocator is going to allocate cake to the first 2 processes and no cake to the third process because there's just no cake left. In contrast, in a universe in which there are no honest processes, which I'm showing here on the right, then both of the malicious processes would have received a slice of cake. So as a result, it's actually very easy for the adversary to distinguish between these 2 universes. So we can conclude that FIFO is not private. Imagine instead that we had an allocator that actually assigns resources uniformly at random. Again, the probability that 2 processes receive a resource on the universe in the right is actually 1, whereas it's much less than 1 on the universe in the left. And what this is basically telling us is that any allocator that is work conserving cannot possibly be private. So work conservation basically means that the allocator allocates as many resources as it can. But actually, turns out that giving up work conservation is a necessary condition, but it is not sufficient. So here we have a variant of random. I'm going to call this random prime, which the way this allocator works is basically it picks a random number of resources to allocate. So either 0, 1, or 2, because those are the possible options that we have. And then once it's chosen that number, it allocates that number of resources uniformly among the processes. And while this specific snapshot that I'm showing here seems to provide privacy, we actually need to reason not about individual runs of the allocator, but about the distributions of allocations. And for this allocator, they actually happen to be quite different. Specifically, a malicious process is less likely to be allocated a resource when there are honest processes around. And this kind of makes sense, right? If there are more people, the probability that you get chosen is lower. So this brings me to a theorem that we prove in the paper, which shows that an allocator cannot be private and live unless the number of processes is bounded ahead of time. So there are a couple of things that I could mean by number of processes. So I could mean the universe of all processes. So in the context of Skype, this basically means bounding the total number of Skype accounts that will ever exist. So you might come up with a bound, let's say 7 billion or 14 billion or 21 billion, whatever it makes sense. The second possibility is to just focus on the active number of processes. So in Skype, this basically means how many dialers will call a specific client at the same time. And so this bound could be significantly lower or like smaller than the bound for the universal processes. So this bound might be on the order of, let's say, 1,000. Or we can focus on just the honest active processes. And so this bound could be even smaller because at least personally, I don't think more than 10 of my friends are going to call me at the same exact time. Now, what we find is that in the first two cases, we can achieve information-theoretic or computational privacy. So the distributions of the allocations in the two universes that I was showing you earlier are going to be either statistically or computationally indistinguishable. And in the last case, we show that you cannot achieve cryptographic privacy, but we can at least guarantee differential privacy, meaning that the difference between the two distributions is going to be at least bounded. So with this in mind, we can discuss a few simple allocators that guarantee privacy under the assumption that we have some of these bounds. And so let's start with a bounded universe. So suppose we have a bound on the total number of processes, meaning that we know every process that will ever exist. So what we can do is we can assign each process a slot. So since we have two slices of cake, we can map at most two processes to each slot. So slots are given by integers here. And the way the allocator works is it compares for each active process their slot number, and it compares it to the current round number modulo 6. Remember that time happens in rounds. And if they happen to be equal, then that process is allocated a resource, otherwise they're not. So this allocator is private because allocations become completely independent of which or how many processes are active. It only depends on whether you happen to request a resource during the round that's congruent to your slot. It is also live because if the total number of processes, so if the bound in the universe is polynomial, then the probability that a process gets a resource is also going to be non-negligible. If we make a more realistic assumption, which is that the number of active processes is bounded, then we can construct an allocator that the way it works is it simply pads the number of processes with dummies and then allocates resources uniformly at random among all the processes, including dummies. And if a dummy gets a resource, then the resource is basically wasted. And so the idea here is that suppose the bound is 3. So it doesn't matter in which of these two universes you're in, there's always going to be 3 processes. And so the distributions are going to be the same. And again, this allocator is also live because if the bound on the number of active processes is polynomial, then the probability that a process gets a resource is going to be non-negligible. There are, however, situations where actually bounding the number of active processes is pretty challenging because the adversary might be able to create an arbitrary number of processes. For example, it can create sybils. And if that's the case, then the number of malicious processes is going to be unbounded. Or maybe there is a bound, but it's a useless bound. Like 2 to the 64 is a bound that's probably good in practice, but it's going to be useless. So we can't use the previous allocator in this situation. However, it is still possible for us to achieve differential privacy if we assume that the number of active honest users is bound. And specifically, what we can do is we can think of these two universes that I'm showing here on the screen as neighboring databases. And we know that the number of entries that differ in these two databases is going to be the number of honest users. And that number is actually bounded. So the sensitivity of the resource allocation function is going to be based on this bound. And the details are, of course, in the paper. But what the allocator can do is that it can sample noise from a Laplace distribution. And that noise is basically going to determine how many dummy processes to add. And then the allocator will just assign resources uniformly among the resulting set of processes. And what we show in the paper is that this kind of allocator is going to ensure that the distribution of allocations under both universes are relatively close. And so we get this flavor of differential privacy guarantee. Now, we can then compare how wasteful different allocators are using a metric that I'm going to call utilization. And so utilization is basically the ratio between PRAs, so the private resource allocators, and the non-private work-conserving allocators. So in this case, a higher number means less wasteful. And to the right means weaker assumptions, so assumptions that are more likely to hold in practice. And the x-axis here gives the bound of active honest users. So in this particular experiment, we assume that the honest processes are 10% of all active processes. So the bound on active processes is going to be 10 times the number that you see on the x-axis. And the bound on the universal processes is going to be fixed at 2000. And so the behavior that we observe from the slot-based allocator is that it's going to be, very wasteful no matter what, because the bound is fixed at 2000. And the other two, we sort of get something that you might expect, which is that as the assumptions get weaker, the utilization goes down. So the allocator is more wasteful. One thing that's interesting is that RRA, which is the random resource allocator, which guarantees information-theoretic privacy, actually gets better utilization than DPRA, which is differentially private. And one reason to explain this improvement in utilization is that DPRA actually makes a weaker assumption, which is that it can tolerate sybils, whereas the randomized resource allocator cannot. So in some sense, this is the cost that you pay for having sybil resistance. So finally, I want to spend a few seconds talking about some of the other results in our paper. Because we're dealing with resource allocators, which are common in economics, we also look into how our definition of privacy affect other standard properties of allocators. So for example, we show that privacy implies population monotonicity. And also in some settings, it also implies group strategy proveness. And we also prove that all of our allocators that I've described in this talk guarantee resource monotonicity, MV freeness, fairness, and so on. In the paper, we also talk about what happens when you want to allocate multiple units of a resource. So for example, instead of allocating one slice of cake, what if you want 15 slices of cake? Like how do you allocate that? And we talk about how to give preferences to some processes while also preserving privacy. So if you want to, for example, if you want some processes that have a much higher chance of getting a resource than others while still ensuring that no information leaks. And finally, we show how to integrate private resource allocators into an anonymous messaging system that prevents allocation-based side channels. And with this, I conclude my talk, and I'm happy to take any questions online.